Hello everybody, warm welcome and thank you for attending this session. Again, my name is Lazar Constantin-Ariton and I am here together with my colleague, Mihai Detesan. And together we will provide you information about how we use telemetry in the automotive context and more specific in the context of driver assistance and automated driving. And of course, you will find out what is telemetry. Now, what we propose here is to give you a bit of the context of the automotive world, to share with you the microservices advantages, then to share with you the challenges of microservices, then keeping in mind these challenges, how we think again on how we apply these challenges on the applications, because we want these applications to be migrated in cloud. And then how we think telemetry helps us foreseeing new challenges that at this moment we cannot see. Of course, there will be a deep dive in telemetry provided by my colleague Mihai, a demo in how we use telemetry in .NET and how easy it is. And then, of course, we conclude our session. So, a little bit of the context. The picture here shows that Bosch aims to keep connection with its products and use data for future development. Since with our devices we target autonomous driving, we want to connect the sensors produced by Bosch from the cars and keep this connection with our products. This is because we want to learn from the data using state-of-the-art machine learning. We also want to update the software from our products in real time with technologies like software over the air. The context in which we are in here in Cluj is the one of frameworks that validate the algorithms running on the sensors from the car. Our focus are the video sensors, both front video sensors and also near-range cameras. In the case of video sensors, in this case, the video sensors are producing large amount of data. Imagine, for instance, that for 1 minute of recorded data, we need a storage of more than 15 gigabytes. Now, can you imagine the amount of data produced by one single car for a small amount of time? Here, I would like to quote one of our architects who said, "The internet is not enough for handling such amount of data." Well, cloud offers us a solution. So for this new paradigm of cloud computing, we need to update our frameworks as well. In today's presentation, we'll focus on the tools that gives us hints how to adapt our frameworks. So let us zoom in and start our journey. Historically, we have developed our applications in the past as monoliths, where all the code associated inside a single process was written using a single implementation language. This happened usually. This made it easy to understand what might be going on at runtime inside this application. We simply attached a debugger or a tracing tool to capture the data, and that is how we actually knew what is happening at the runtime inside our process. However, as internet became a greater place and our applications needed to grow and scale in complexity, in order to meet our demands and the expectations of our customers, architects realized that we need to have an approach where we need to break up and decompose monoliths into small interdependent services. And this is where the microservice architecture really started to take off. Well, microservices are for scaling people, partition the organization along the boundaries of their services. For instance, I can have a service using a set of tools and another service implemented using a different set of tools. And those two services can interoperate with each other because they all work using explicit communication networking contracts like HTTP or HTTPS. So what this allows teams to do is still build a network application that can accomplish the big goals that organizations have. The advantage is that we can develop, deploy, and update each and individual components independently of the others. So this microservice organization really allows our software organization to be more agile and to deliver products faster to our customers. So it is easy for us to deploy and develop software, but this easiness doesn't come without a cost. So let us take a look at the microservices problems. All the monitoring and tracing infrastructure needs in a monolithic application is to tell the story how the software ran from the perspective of a single process. All the data and why a specific request succeeded or failed is all right in there. It is easy to get to that data and really easy to tell the story using tracing tools. So this happens for a monolithic application. In microservices, however, this is no longer true. The first big problem that we have is a loss of coherence, where one service makes a request to another, maybe that service makes a request to another service downstream, and so it becomes very difficult for us to trace where exactly a particular request fails. Imagine this kind of failures in case of an integration process. Also imagine what happens when a service doesn't fail, but the result returned is not correct. Now, these kind of failures may happen in case of .NET's microservice that returns a failure to another microservice which is Java-based. In this case, the propagated error may be lost. For example, think about an error code of 200 where it states not found. Now, regarding debug difficulties, it is pretty hard to synchronize all teams to use the same structure of a JSON file. In essence, without having some standardized way of being able to get data from each of the processes that participated in a given transaction, it can be very difficult to figure out what went wrong and how to fix it. So in the great schema of things, what microservices can really do is to end up creating communication problems for you and for your team. And it can be very difficult to go and track down where the problems begins and where the responsibility is to fix it. And all this come with a higher human cost. The very thing that made it so easy for us to deploy and develop software also makes it harder to debug and diagnose it. So now, keeping this in mind, let us take a look at the use case. Here is an application that we develop on our side with the purpose of indexing, creating queries, and display the results of these queries. The input of the application are, first of all, video files. I want to remember you that here comes into play the dimension, the big dimension of the files. So here we speak about big data because, like I said previously, for 1 minute of recorded uncompressed video, the storage space may be more than 15 gigabytes. So in order to give meaning to this data, we need to extract them first. Then we want to enrich them either with GPS location data or vehicle information from other sources of data, like you see here, Bosch IoT Insights, or simply by adding the output of machine learning algorithms with regard to specific detections that happens inside of these machine learning algorithms. The following layer the following layers actually, because we are talking about the layer in which we see here Elasticsearch and MongoDB, and also the layer of presentation. So in these layers, what is happening is actually indexing the data extracted inside the ETL process, and then queries are built using the UI in the presentation layer. So our focus is to be able to extract as much data as possible. We also want different teams to be able to integrate their own libraries independent of the programming language chosen. We want this because we want to scale to other types of data coming from other sensors like ultrasonic sensors, radars, and so on. Of course, we want also to deploy these extraction services because we will focus on the ETL process to the cloud because of the cloud advantages. So let us zoom in the ETL process and see what challenges brings the microservice architecture. Here you can see side by side two architectures, the old one and the one that we want to deploy at some point in cloud. And of course, we want this second architecture to scale both up and scale also out. Just to remind you, scaling up means adding more computational resources, while scaling out means having more instances of the same service. As you can see here, we have an event bus, so therefore the communication between these services is through events. Now, the following questions emerge having the mindset of the challenges that I described to you above. What if we have, for instance, thousands of video recordings coming all at once? How much time does it take for a file to be processed end to end? Where can we see these bottlenecks? What if the order of the execution of the services matters? What if we have a third-party services? How can we trace these behaviors? How can we instrument load balancing? Well, to answer these questions, first we need to see the services running, and then we can decide upon the actions to take and how we can scale the architecture. Well, for all this, we consider that telemetry is a way of getting the answers to these questions. And now I would like to give control over this presentation to my colleague Mihai, who will get into the depth of telemetry. So Mihai, you have control.
Hope you're seeing my screen. Okay, so to actually answer the initial question, what is telemetry? So we have a short definition in which we talk about measuring at the distance an instrument. And of course, in the context of distributed applications, the instrument is an app or a service or anything else related to software. And what do we do with this telemetry data that we collect is get a state of our application. And with the help of telemetry data, actually, we get to achieve observability, which is a term from the definition. You can see that we can get to know about our distributed app from its outputs. We get to know what's wrong and why, or what's the current status, what's happening actually inside. So if we just think about a desktop application or a monolithic application, what you did in order to debug an application or to know what exactly went wrong, you would look at the logs. You maybe had some profiling performance. Of of course, you would go into debug, you would see who called whom, and so on. And something similar needs to be done also for distributed apps. So for observability, they have been defined three important pillars, or major pillars. And these are the types of data that we can collect with telemetry. So on first, you have metrics, which give you an overall health of your application, statistics of what's going on, what is the load, how many services are in action, and so on. Then you have traces, which give you a map or a picture of who's calling whom and who's responding. And then you have logs, which give you detailed information about certain events that happen in your services. And just having these three types of data is good, but sometimes it's not good enough, because you have to have a bit of correlation between them. So, for example, having traces and seeing who called whom, maybe it's helpful also to link that to logs, to a log entry, and see exactly what happened when something was called. Or between metrics and traces, it's helpful to add some metadata to the traces and see exactly what version of the service was responsible for an action. So here I'm stating just some suppliers, some software suppliers that we encountered. There are, of course, many more, but we encountered this, like for metrics, very famously, probably if you're looking, you will see Prometheus. Or for, of course, as we are working in .NET, loggers, we use nlog, serilog, or of course there are other solutions as well. For the traces, very popular ones are Zipkin and Jaeger. And of course there are some software providers which are covering all three pillars of observability, they are doing the complete job. We are going to focus on Open Telemetry, because this was the solution that we used in our example and in our future architecture. Open Telemetry will handle the parts related to metrics and to traces, and will help correlate with the logs. And what is Open Telemetry? Basically, it's an observability framework, which comes from the merger of two previous frameworks for tracing, which are OpenSensus and OpenTracing. And the advantages of Open Telemetry, or why we chose this one, was because, first of all, it uses a standard way of adding trace context. And this is specified by W3C in one of their documents. We will discuss this a bit later. It is open source. It's very extendable, so we actually use that feature, and we extended one of their instrumentation libraries. It is easy, very easy, and we will see that in the small demo that I prepared. It is easy to plug in into a .NET Core application or service, and it has loads of instrumentation libraries and exporters, of course, including also the very popular ones. What is not, because this is an emerging solution, it is not complete. So metrics will be available starting with September. Right now you can play with them, but it's just a branch. So they are still working on it. So of course, because of this, also the interfaces are not that stable. So in September, you might have a release product which has also metrics. From architecture point of view, they offer, like I mentioned, a lot of data sources and instrumentation libraries for different types of communications. I'm just listing here HTTP, gRPC, they have Redis, they have Mongo, for example. They have the ones that come out of the box when you get the the distribution for .NET. They have, of course, I forgot to mention this, they do this for different languages as well. So you have one for .NET, you have for Go, you have for Erlang, and so on. But we're talking about .NET here. So you have ones that are coming out of the box and one which are developed by other contributors. And we did also some for RabbitMQ, which was our preferred communication between services solution. They use, like I mentioned, the exporters, which are very well used right now for tracing, which are Jaeger and Zipkin, the two solutions, and for metrics, which is Prometheus. They have the possibility of having a collector service, which interacts with the backends. It is an independent service, and it communicates with your applications with a protocol, and then communicates with the backends, with Jaeger, for example, on its own. But they have also the solution that we chose it's highlighted here with red, to export directly to the backend. So don't use an open telemetry collector service on its own. We directly communicate from our service to the backends. And this is the solution that we chose. Okay, and so now I want to build a bit of introduction about tracing, because I discussed a lot of tracing, and now I want to show what I mean. So we have an example of, I just took an example of services that would call each other. And you need to have some sort of image to see exactly who calls and who gets called, and how is this done in your environment, which might be very crowded with a lot of services and versions of services. So in order to do this, what every vendor thought about is having an end-to-end communication ID. And in this case, we call it the trace ID. So this remains stable on all levels. So from service A to C to D to whatever other, you will have an identifier of your current operation. And then you have to have a parent-child relation, so that you see who called and where does it stop. At the end, you have, of course, the trace collector, which might be custom, might be the open telemetry one, and you have the trace collector, which gets all this information and builds some sort of a graph, or a picture of what is going on. Until now, using just one of the two main ones, Jaeger or Zipkin, meant that you would implement their way of instrumenting this trace IDs. So now the advantage of OpenTelemetry comes that OpenTelemetry uses internally a standardized way of instrumenting this, which is defined by W3C. And then it exports to Jaeger or to Zipkin in the way it expects. Now the advantage is when you're switching from one to the other, you're just switching one line of code, like, oh, I want to export to this, or you might even have both at the same time. I want to export to both of them, and then I'll see how I'm working with this. So the advantage is you don't change now the how the instrumentation of the traces is done. Okay, so I talked about this W3C instrumentation, and I want to show from their perspective, at least from HTTP communication context, how it should be done. So they proposed adding two extra headers to an HTTP communication, and one would be trace parent, in which you would have as important fields, you would have a trace ID, which is the end-to-end communication identifier. And then you have this doesn't change from one service to the other. And then you have a parent ID, which, as you can see also from my graph, it changes from service A at service B, at service C. You're already sending another identifier. Okay, the other ones is a version, and the last one are some flags which tell you if it's a sample or non-sample collection of activities. I mentioned activities because that's how we do it in .NET. So you don't really need to know about this unless you're writing your own instrumentation library, because it's done behind the scenes by the library provided by OpenTelemetry for your communication. What I missed is the second header of which is of importance is trace state. So sending this traces is good, but maybe sometimes you want to add some metadata to identify more, even more your service. And for this, they defined another header, trace state, which allows you to add pairs of key values, which you can transmit only to your next child or throughout the entire operation if you want to. There are differences between the two. And all of this can be done with the system diagnostics activity class if you're writing your own instrumentation library. And you have here the fields defined as trace ID. You have in activity, you have another property which is called span ID, which is the equivalent of parent ID. And the good news is that already from .NET Core 3.1, I think, they're already in the format, or they are compatible with the format defined by W3C. So you don't need to do anything about that either. In older times, I think you had to switch the context format from whatever hierarchical to this W3C. Okay, now that you have an image of how calls in your services are done, you get to logging to the details. So you have a map of who's calling whom, and you identify your breaking point of your application. And now you want the details. So you have your services, and very important, if you didn't know until now, but it's important to log and to send all your logs to a common location. You can keep them locally as well, but just keeping them locally makes it harder for you to just run around from machine to machine, from server to server, to see, okay, now this server is broke, and now I need to go there and get all the logs and see at what timestamp did this happen and what happened. So it's better to store them all in one location, and we use Elasticsearch for this. And you would say, okay, I'm sending some details and I'm querying them, and am I done yet? Well, not exactly, because what you're sending would be what? A timestamp, a message, a class, a function, whatever, an exception message, and so on, or whatever message that you want to see. It's maybe helpful to send a context of your service, like name and version, and to bring it all together with the previous image of the calling map. Maybe it's helpful to also send a trace ID. So now you identify for sure that this log entry is referring to exactly your operation that went wrong. So now you have correlation between logs and traces, because I mentioned correlation at one point. This is one point of correlation, and this is done easily in .NET, because then when you're writing the logs, you just have to add this current, which is a static property for the activity, and then you just say current trace ID. So whatever I'm doing now, whatever activity am I in now, I just put the trace ID, the current trace ID, and then I'm done. Okay, I will just show now what example we prepared or we worked on, a reduced example of our full architecture, ETL architecture. And what we have is 3 services. We have a watcher, that just looks for events, so new sequences or new files, new data files that are being stored in a location. Let's call this epsilon. And whenever there's a change, it will grab this and send it over RabbitMQ to the extraction service, which will in turn get this information. We will try to do some extraction operations. Of course, extraction it's very abstract because there might be more than one extraction service. This is, like I said, this is a reduced example here. It will do some extraction, and then also over RabbitMQ will send this to a writer service, which will store this to a MongoDB backend. We will have also, after this, some enrichment, some presentation services, but these are not the focus for this example. So what do we do to monitor this? We have a trace collector service, which is Jaeger, and we send this with the aid of the instrumentation exporting that we have with OpenTelemetry. We have the logs, and we send them to an instance of Elasticsearch. We also send the traces back to Elasticsearch because Jaeger does not have out of the box a backend. So there must be a connection between the two of them. Okay, now all of this is fine and nice, but there's need to be some monitoring, some observing and some monitoring. So some alerts, some events that you might be looking for, or if you're in the development phase, you just look at what happened, what traces were being sent from one service to another. And for this, we stopped on Grafana. There are many other solutions, but we are using Grafana for this. Okay, this would be it. You will notice that one of the pillars is missing from this, and this is not the purpose of this presentation. We are missing metrics. Because OpenTelemetry is not done with the metrics part, we didn't want to show this. Of course, you can do this simply by adding Prometheus to your application, and then also Grafana can monitor that as well. Okay, so now if we look at the contents of a service in .NET Core, from our perspective, would be just having the useful code that does something, extraction, watching, writing, stuff like this. We have the logging, which is provided to us by nlog, and we have an extension that allows us to write to Elasticsearch. We have the instrumentation, several instrumentation libraries that we use from OpenTelemetry. We have an exporter also provided by OpenTelemetry. We have the RabbitMQ communication, and we have the instrumentation, which is exactly the custom library that we wrote in order to add context to RabbitMQ messages. Okay. Now, if I will just switch to Visual Studio, I want to shortly just show you how easy it is how easy it is to add this to an application, to a service that you're using. So basically, all you need to do is this. You add OpenTelemetry tracing as a service, and inside you add your sources, add your instrumentation sources. Out of the box, you can use HTTP. You can have .NET Core, you have gRPC, and so on. We are not using that. You can use your custom one, which is this is the RabbitMQ for us. You have your exporter here, and you're basically kind of done. Anybody who used logs before, you can use your nlog as a logging service, and this would be it from your coding point of view. If you're interested in this, we can also show later what's how to instrument a library for a RabbitMQ. But if not, okay, I want to show maybe also what do we do to export to Elasticsearch. So this is a normal configuration for nlog, and you just use this extension, and then you put the target to Elasticsearch. So then you're done, and you're sending your logs already to a common location. Good. Now I will switch to Grafana, and hopefully this all goes well. We go to data sources, and you can see here I have configured already Elasticsearch, Jaeger, and Prometheus as input sources. There are many others that you can monitor. And if I go to the exploration part and I look for, I don't know, in the last 2 hours, 2 days, for Jaeger, for the traces, and I watch, and I'm going at the watcher, and I look for this, I can show that the traces for one of my operations looks like this. So you remember what services I described. You have the watcher, it goes into the extractor, and you can already see also how my application is modeled actually. What's waiting for what. You have an extractor, you have a storage writer, you have the MongoDB also instrumented here. If I look into one of these, I can see this didn't went well, so I couldn't write to Elasticsearch for whatever reasons. This is the endpoint that I'm trying to access, and it didn't went okay. Then here, I did not send any tags, but let's say I could have added more information if I wanted to. Of course, sending so much information in the tags and as baggage poses also a risk from security point of view. So you need to be careful also about that. Okay, so this would be how the traces look like, and you can see at the top of this there is a trace ID, which is the identifier of my entire operation. Okay, if I switch now to the view of Elasticsearch, I can look for the logs in the last 2 days, and I can just focus on this, and let's see what I've been storing. So this is the storage writer, so the one that writes to MongoDB. I have the information here. I have the version. Of course, this is an example, so it doesn't really have a real version behind it. There is a machine IP also. Again, be careful with what information are you sending and the amount. And you have the trace ID. Now you can connect the two of them. So you just switch to Jaeger, you go to whatever went wrong, if it went wrong, and you search for this. And you see, okay, is there any detail about this particular operation? We have the extractor here sending the contents. Of course, the extractor is a very basic, just an example written, so it doesn't do any of extraction. It just writes the content, reads the content of the file, and sends them forward. So, as this is just example for you. The same watcher, at one point we have the watcher which just detected, okay, this file has been created, so I'm now sending. So now you can see also the operations in the log way. Okay, so I hope you liked this, and what I would like to have as a conclusion from all of this is that it's important to start early with this. So whenever you're in the design phase and in your development phase, you should start early with adding this kind of features to your applications, because it helps you in the development phase, in the testing phase, and it helps you also, of course, later in the production part, in the monitoring part of your application. And we chose OpenTelemetry, but it's not an important which solution you choose, as long as you go with one and then you are able to monitor your applications. So, and yeah, remember, be flexible. I mean, when you're starting the development, you can look at several. You can switch at one point with monitoring. I can switch to Kibana, or I can switch the database from MongoDB to another. But it's important to keep this in mind, to be flexible and to go as early as possible with this telemetry implementation of your microservices. That is it from my side. Thank you. And yeah, if you have now any questions related to this.
Guys, first of all, congrats. I mean, I personally enjoyed what I've seen. I mean, it looks like a very nice blueprint. I was discussing with Dan, the way you presented it, the way you thought about it, really useful for us. And I bet most of the audience feels the same. The question I had would be, what were the most challenging things while building this entire infrastructure and architecture?
Well, from my point of view, and I will let then Ariton continue. From my point of view, is choosing the right tools for your particular solution, because there is no silver bullet. There is no technology that fits all organizations and all needs. So for me, this was most challenging. So you have to invest some time to really look what's the best for you and what works better for you, for your knowledge, for your team knowledge, and so on.
Mm-hmm. Okay, so the tooling.
The tooling, but there's also more than this. It's also the decision, and by taking a look at the architecture, which solution fits best in the architecture. Also keep in mind what Mihai said previously with regard that we need to start early when detecting errors, because errors propagated down the line towards production, they become more and more expensive, both costly and both time-wise.
Mm-hmm. In terms of the effort that you put in this and the team that created this, can you share something? I mean, was it like you two guys, two strong engineers doing it, or because this is a solution that needs to be communicated, well understood in the team, and probably there are many other stakeholders around. How did you manage the entire situation?
Of course, so the team is much bigger, and inside the team we have architects. Inside the team we have a DevOps mindset, and together we took this decision how we can put everything together and how we can actually catch errors early and create a bridge between these errors so that we don't lose them. So the project itself started some time ago. So we kind of knew what to expect. And then now we are at the point that we want to merge everything into microservices, merge the use cases and the implementation into microservices, and then deploy these microservices in cloud. And then we are now at the point, okay, we are splitting everything. What are the issues we may face when developing microservices from this application? And with regard to that, we try to catch all these issues early, like we said, and we try actually to see where the architecture or the microservice architecture has challenges for us, and we think OpenTelemetry is the way to find out, let's say, weak spots in the architecture.
So could you please share maybe a little bit about how does the deployment looks like? I mean, how much is like, I don't know, fast so using services, or how do you deploy the application? I'm interested in the your solution compared to what's happening already in the cloud, like the Azure Insights, or was that not enough for you? You felt like you need to augment with
So yeah, basically there is always this way of thinking in terms of serverless, in thinking of functions. So rewriting everything in functions. So currently, at this moment, we are in the phase of taking the decisions where to switch to functions, where to actually create web services, how to containerize using Docker, where to use these containers, and then how to put everything in place. But before everything, we need to find the weak spots.
Got it. You mentioned security at some point. How do you handle that? Security is well, especially in your industry.
It is quite a strong point to think about. Well, currently our focus now is not on security. This point will be taken into account at some point, but now our focus is on data engineering. Now our focus is on the frameworks themselves. And then, of course, there will be a security engineer that will handle this, security topics, will handle the gateway between the militarized zone and the Azure and so on. So currently our focus is just on the frameworks.
Super. Anything else you'd like to share with the audience before jumping into the break?
Yeah, so like Mihai said, start early, think having put all the things together, and also think about the architecture with a DevOps mindset.
And if I may add, stay strong and bear with us till the end of the day, because there is more stuff to come. Thank you, guys. We really appreciate your contribution and enthusiasm. I mean, is it sunny outside? Yeah, it is, but I like it's brighter now, seeing all this passion, and yeah.
Thank you very much.
Well done.